All right. So the first tutorial of the day is going to be on testing scientific software, in particular with pytest, and that'll be me, I'm Nick Murphy, and Michael Hirsch. All right, so this is going to be a two-part tutorial. I'm going to start off by giving a high-level overview of our motivation. Why do we test scientific software? And then Michael's going to go into a bit more detail about using pytest in particular to test Python code. All right, so one of the main points, one of the main takeaway points is that well-written tests make code actually more flexible. If we don't have tests, if we make a change, we might unknowingly introduce a bug somewhere else in the code. And without tests, we wouldn't be able to have a way to check that straightforwardly. And because of that, at least in my own experience, we're less likely to change code for fear of breaking something. But if we have a clean test suite, we can find out if a change broke something. So that helps us make changes to the code. And we can track down bugs more quickly. And there was a quote from a book, Working Effectively with Legacy Code, that legacy code is code without tests, because that makes it really hard to change. So why do we write tests? Tests help us get confidence that our code is giving correct results, which is important for scientific software especially. And tests help us define what the correct behavior actually is. So if there are edge cases, we can define what the behavior at those edge cases is supposed to be. It helps us catch and fix bugs, and preferably as soon as we introduce them. If we catch bugs a few months after we introduce them, they're a lot harder to fix. We can also sometimes write tests to keep track of bugs that we plan on fixing later, or tests for functionality that we plan to write later. So we can mark these tests as expected to fail for the time being. Tests also end up being a form of documentation. They're a way to show future developers how code is intended to be used. And we write tests so that we can change the code with confidence that we're not introducing hidden bugs somewhere else in the program. Right, so here's the anatomy of a simple software test to test the Douglas Adams number from Hitchhiker's Guide to the Galaxy. So we have a descriptive software name, or name of the test. We have a descriptive description, a documentation string. We have a check that a condition is met. And we have a descriptive error message if a condition is not met. So there are a bunch of testing best practices that are worth keeping in mind. It's helpful to write assertions directly into our software. So some checks don't actually have to be part of the test suite. They can be built into the code. So if we have a variable positive number and it becomes negative, then we can raise an error. Another helpful practice is to turn every bug that we encounter into a new test. And that has some advantages, like telling us when that bug is fixed. And it prevents that bug from happening in the future. In addition to testing bugs that arise, we can test potential related bugs to the bugs that we found, because bugs often happen in clusters. It's also really helpful to make tests deterministic. So if we have a test that fails intermittently, then it's hard to tell if that test is that the bug is actually fixed or not. So it's important to do things like use the same random seed for tests that depend on pseudo-random number generators. And the biggest thing is to run tests often. If I end up making changes for an hour and don't run the tests in that time period, I usually end up regretting it deeply. If we run tests often, we can find bugs quickly, like when we introduce them, essentially. All right. More difficult question is, how do we know what tests to write specifically for scientific software? So we can start off by testing some typical cases. Then we want to write tests for the special cases. So if we have a function that has some weird behavior near zero, like if it goes to infinity at zero, then we should test at zero to make sure that it's behaving correctly, that it actually does return infinity. It's important to test near and at the boundaries. So if a function requires a value greater than or equal to 1, we should test at 1 and then also near 1, so at like 1.001. We also want to test that code fails correctly. So we have the same case that a function requires a value greater than or equal to 1. We should test at 0.999 to make sure that it's raising an error as we're expecting it to.
Can I make a comment here?
Please.
I because I didn't have this in my slides, and this is something I just thought of. So what I was shown to do a while ago or 12 years ago is that when you have, say, transcendental functions or sine and cosine, things like that, that may have, especially when you have ratios of those things and squares that may get oscillatory and things like that. What somebody showed me to do years ago was test by approaching it, let's say, with powers of 10. So first you say, like, let's say you know it's going to blow up at 0, let's say, or at 1 or whatever, or pi or whatever it's going to be. Approach that with powers of 10. Like first you say, pi minus 1, pi minus 0.1, pi minus 0.001, and so on in powers of 10 until you get like, pi minus 1 to the negative 16th power. And that can show you, because what people will sometimes do is they'll say, oh, if this value is less than epsilon, drive it to 0. Now, what that can do is that behavior can be okay, but it can also make, sort of a step function, like suddenly the error like jumps all of a sudden when you force a value to pi or 0. And so when you test like this, when you test in those, let's say, powers of 10, subtracting powers of 10, so you get, approach that value where it's going to blow up, or you know that you're going to say, oh, okay, if the value is, like we might say, oh, if the value is pi, just set it to nan or set it to 0 or something, or but that's a way, like, kind of, slowly approach that to test that, you or someone else. That's because that's basically what happened. They said, hey, your code has this big jump when you get within, if you're like, 10 to the minus 5 to 10 to the minus 6, suddenly there's a jump. I said, oh yeah, I set it to 0. But they said, yeah, but it makes the code behave bizarrely, so make it, transition more smoothly. Anyway, that's just a tech. Forgot to put that in my slides, and this brought it up in my mind.
Yeah. So yeah, that falls into the category of testing near and at the boundaries. So it's approaching the boundaries closer and closer. So, all right. And then to give some examples for numerical modeling in particular, we can test against exact analytical solutions. So things like making sure that an equilibrium condition actually behaves as an equilibrium, or waves, making sure that those behave correctly. Oops, that is a repeat. We also want to test against conservation properties. So things like conservation of mass, momentum, and energy, or whatever ends up being conserved in the situation that you're looking at. We should also test things like convergence properties. So if you have an algorithm that is supposed to be fourth order accurate in space, then we should make sure that it actually is fourth order accurate. So testing properties that are expected. And you can do that by decreasing the spatial resolution by a factor of 2 a couple of times to make sure that the error drops to the fourth power. And then we also want to test limiting cases. Another underappreciated question is, how do we write testable code? If we want clean tests, then we need clean code to go along with it. Probably the most important thing is to write short functions that do exactly one thing with no side effects. And that allows us to test the behavior of the individual functions. A function that does many things is a lot harder to test the behavior of. Again, writing code that's deterministic. So having a way to input the random seed for that you use in a pseudorandom number generator. It's also important to create clear boundaries. If we don't have boundaries, then we don't have a place where we can test things. And along those lines, it really helps to avoid global variables. So something that is defined throughout the course of a program. We want functions to be local and depend only on local variables, like what's the arguments that are provided to them. And it's also important to minimize the coupling between different parts of the code. So if you have code that ends up being really tangled up, like different parts, the connections to the code end up looking like spaghetti. That makes it a lot harder to test. That's especially true for legacy code. Another practice that is underappreciated in science is test-driven development. The most common practice, what we usually do in science, is to write a function and then write tests for that function and then fix the bugs in that function. In test-driven development, the alternative is to write tests for a function first, then write and edit the function until tests pass. And this has a couple of advantages, that it makes us think ahead of time of what each function will do. And also, it often ends up saving us time. Often when I don't use test-driven development, I end up regretting it about half an hour to an hour later. So it often ends up being a really helpful practice, though not necessarily always. If you're playing around with a prototype for code, then this might not be the best practice, but in general, this is a helpful tool to have in our toolkit. All right, that's my last slide, so I'll pass it on to Michael. If there are any questions or comments, we can do that now.
You know, what stuck out to me was your advice to write functions without side effects. And that immediately makes me start thinking about functional programming. I'm wondering if that's something either of you two have dabbled in.
To an extent, the idea behind functional programming is to have our code be pure functions. So if we provide a set of arguments to a function, we'll always get the same value that's returned, and it doesn't affect anything else in other places in the program. Yep. And that ends up making code a lot of the time cleaner. So there's something to that if we can write a pure function, we should. But there are other times where other programming paradigms end up being more helpful, like object-oriented programming. Mm-hmm. So it depends.
Sorry.
There are different programming paradigms that we can use and testing strategies that work in different situations.
Yeah, and Python is not the most functional language out there, so I wouldn't expect everyone or really most people to be dabbling with functional programming in Python specifically. But I always like plugging it for scientific use cases because, like you pointed out, it's really nice to know that you're going to get the output that you want given the input. Makes things a little bit more scientifically sound, easier to reason with, etc.
Yes, this is very true. All right,
That was my comment.
cool. And if there's nothing else, then I will pass it to Michael.
Okay, there we go. Well, great. So Nick was talking about sort of what I think of like more of the theoretical side. Like here are these principles that are beneficial, whether you're doing testing or not. You know, having a, especially the comments there in his last slide would help anybody. Sometimes though, we come into programs, including especially in our field, where we have. I'm just going to find my. And now, actually, I was going to show you this file. This is a model called Lotran. It's an atmospheric model. That model, one of the things it does is it models absorption bands in the atmosphere. Like, say, if you're looking from the ground to space, or space to ground, or laterally, or at some angle. Now, I can't actually, if I click on this link, my browser will freeze. This is about a megabyte. The Lotran program is contained mostly in this single file, about a megabyte of code, tens of thousands of lines, and I actually, even in a modern, like a good computer with Microsoft Edge, it will freeze the browser, so I can't show it. But I'm saying that was right back then in the 1980s. I mean, they did a tremendous job. But they did break it up into functions and stuff. But and nowadays we kind of go a little bit to the other extreme. So let me come back to the presentation here, and let me just see that dying. Is that still showing the slide? Yep. Okay. Thank you. So a brief outline. Why test? Nick got into that a little bit, and then we'll say why pytest. How to discover tests. I'm sorry, how pytest works. That is how pytest works to discover tests. As I'm going to talk about, other programming languages also have their own test frameworks that work in at least analogous ways to pytest. Then we'll dive into a few features of pytest. Obviously, there's more than this, like pytest hooks and using mocks and things like that we don't maybe have the time or the scope to get into today. And then finally, we'll touch a little bit on continuous integration. So I have only about 24 slides, so I thought I'd do like Nick. It paced a little bit for interaction, and I would love to have you guys jump in and say, maybe I missed something or something I didn't emphasize, or if you'd like to chime in, please do so. So yes, this is a little bit more, more about the how versus the why. So, but what we do discuss here a little bit. We test things. Maybe we'll test the whole package. Maybe we'll test individual scripts, like example scripts, and certainly we'll want to test like functions and methods inside classes at the very least. So what does it just say briefly? What's a test framework? I think of it as it's orchestrating independent tests. I'm going to just my video wasn't on here. Sometimes it's helpful to have video. Okay, so it orchestrates tests. So you can write tests without test frameworks, and what you either have to do, so I do this in Fortran sometimes, like where a customer doesn't want to use the PF unit or one of the Fortran testing frameworks, I will write a bunch of little test programs. So what I'll have like maybe 50 little tiny programs, and they test different functions or modules in this. And it could be not, it wouldn't have to be Fortran, it could be C or whatever language, it could be Python as well. If for some reason, I also work on projects where they want nothing but the Python standard library. And so in that case too, sometimes I end up writing, doing some tricks and techniques like that there. But that's one way to do it. Now, if you write 50 different, let's say for the Fortran case, or C, whatever language you prefer, if you write 50 little tests, now how are you going to do that? You're going to sit there and type a bunch of things, or I guess you could make like a Python script or a Bash script or a PowerShell script to run all those. That's a little bit tedious, and how are you going to track like when they fail? Like you got to like scroll through all the text, or you got to end up you end up writing your own test framework basically. So when you can, it's convenient to use built-in test frameworks. So now what I do sometimes, very often when we have a compiled language program, we have a build system. CMake is very popular. There's others, of course, like Mason and others, but I'll just mostly discuss CMake. So CMake can run those 50 tests for you, but we're talking more about Python here today. So, and we'll get into the PyTest framework that's popular. So, as Nick was saying, in general, we don't want to share state, ideally, unless it's your intent. We try to avoid putting state into functions. We like to hold, if you want to hold state, hold it in an object or hold it in a particular variables. In general, we try to do less. We try to avoid storing state in functions. So in the same way, certainly with tests, like we don't want to have tests that are contaminating each other. So when you have a test framework, it's been carefully written to avoid sharing state, unless you want to. Sometimes you do use methods to share things between tests, but you don't want to do that. You don't do that unless you're explicitly doing it. And even if you're running tests in parallel, like I have Python programs where I'm running like 250 tests, and each test takes a little while. So if I have an 8-core machine or a 16-core machine, I'd like to use those 16 cores and not be sitting and waiting for 250 tests to run when I could be using the whole CPU in my machine. So the frameworks will help you do that as well. Yeah, so one failure. So the reason why I write in a compiled program 50 little programs is I don't want, if one fails, I don't want to like, oh, okay, now I have to fix that bug before I fix anything else. Whereas if I have all those little 50 tests or 100 tests can run independently, or if one fails, the rest can keep running. Like then I'll know. So if I run my test and I see like, oh my God, like 90% of the tests fail, okay, I must have goofed up something pretty fundamental. But if I have a test program that I write myself and it stops at the first crash, well then I won't know. Like was it something particular to this, or what's going on? Like I don't have an idea, a sense of what is broken. Like when you see like an enormous amount of tests fail, you say, oh, okay. It starts to give you a hint about where to go. And maybe that sounds trivial at first, but as you start to use it, it's basically a method to save time. It gives you hints about what's going wrong before you have to like actually sit and scroll through all the little messages and debug. So test frameworks, when you use them, also help you just save debugging time. There is an exception to that. I just want to say to that third bullet point, the fourth bullet point is a bit of an exception that for cases you may have early tests. I try to write tests this way that check fundamental things like, oh, the GPU driver is broken, or you're running it on a Raspberry. I intended this to be run on a laptop, and you're running it on a Raspberry Pi with 1 GB of RAM, or something, that's maybe not an appropriate system, or your MPI library is broken. Because when you run a program that's using, let's say, some of the more complex frameworks like or libraries like MPI, you can get like these really confusing errors and like things that, oh, it looks like the program is running, but it gives you weird results, and you think like, oh, it's a bug in my code, and it's actually just that MPI is like somehow goofed up, and maybe there's that needs to be fixed. So if I'm doing something like if it's a complex library, something like mumps or whatever library I'm invoking, I try to test that library, even though it's not my library. I test that it's working, and I write at least a few tests just testing that, so I'm not. And that's because I used to not do that, and I would get very confused, and I'd have to do extra debugging. It's kind of when you write these tests well, especially on more complicated systems, they'll kind of like do a little bit of the debugging for you. They'll not do the debugging for you. They will give you really good hints that save you debugging time and like thinking like, oh my gosh, what did I break? Skip here. So I did give credit here to the MathWorks for this. I thought it was nice. I was thinking recreating it, but they did just such a nice job of this here. Unit test versus integration test. The integration test, I think these terms are fluid a little bit. People define them differently, but I think of an integration test as testing pathways through multiple modules. So I think of it more a little bit like the test on the left, where we're going testing multiple pieces together that they work. And a unit test more is where we're testing sort of the atomic unit of the program, things like a individual function or something that. So to do that, generally you need, this is where mocks come in. Now, Python has a mock module that some people use quite extensively. I don't as often use it. I end up kind of making my own test data. Maybe I should use Python's mock module more, but you do have to provide it some sort of simple, repeatable inputs and outputs that check, inputs and then check it against the outputs. And we'll talk about using parameterization, where imagine that this blue color is also pink. Like, so my test might be blue, pink, green, fuchsia, whatever. We're going to test many inputs and many outputs, bad inputs, good inputs, unexpected inputs, wrong types, and that will help make our function more robust. Because what we tend to do is we tend to write the tests that on things that we expect to see. At least that's the way I do. Like, it's like, oh, I expect to see this, I expect to see that. Then I get GitHub issues, when I do my releases, and it's like, oh, I didn't think about doing that. But then I have to address those kind of issues. Can you I have to pause for 30 seconds here. I've had a guest walk in. I'll be back in 30 seconds. Okay, there we go. Short break. There we go. So when we, so the unit test is more here on the right, testing individual pieces, but it's also important to do integration tests to be sure that segments of the program, oh, yes, oh, sorry, I'm certainly unmuted. to test that meaningful segments of the program work correctly. And then finally, you might do validation tests. Like imagine these puzzle pieces here are a whole system. You might want to validate the whole system to be sure that it meets grant or contract specifications. Okay, so now let's dump in, do a little bit more specific here. So by coding language, I just listed a few popular languages that I think are used in our field. I probably left out some favorite ones. I mean, I know for like C and C++, there's an enormous amount of frameworks, so I didn't mention those, but possibly left out your favorite language. But I'll just start over here on the right. Like IDL, I think as far as I know, I'm not a daily IDL user, but as far as I could see, there wasn't one built in. There's this MG unit, an open source framework. MATLab's is built in. I do use that. I think I give an example in a later slide from MATLab. GNU Octave is also has a built-in one, but it's totally incompatible with MATLab. That's unfortunate, but I think we probably more people are using IDL and MATLab versus GNU Octave, although I do support GNU Octave. Fortran mentioned PF unit. So Python, we have unit test in the standard library. I've seen some people in PyHC community using unit test. So this is maybe a little bit oversimplified, but I think a pytest of it's compatible. Like if you already have, I've worked on projects where they already had like over 100 tests in unit test, but they were getting like they felt a strain, like they wanted to test more, but the syntax, and this is again just a personal opinion, that the syntax of unit test was just a little bit limiting for what they wanted to do. And I said, hey, look, like let's try pytest. First of all, it worked, like just dropped right in. It worked with I think almost 100% of their existing unit test stuff. But now I could add parameterizations. I could do things that were like made their code test coverage go way up, and it actually not just the number, it was actually the meaningful test coverage was able to go much higher thanks to pytest. And again, so people like unit test, I want to be very respectful of that, but this is just an option that's out there. That's what we're going to discuss. So how do you do it? So Nick is saying like, here's all excellent ideas about these are principles and principles that we should aspire to use. How do we do this? So this is one approach I take. Every project's unique. I like to think about making a registration or a validation test, whatever language you want to use there. Test the whole project. Now, even legacy, I don't say legacy, like what I need to say is like long-running projects, like MSys and some of the big models in our community, or the parameterizations and models in our community. They do have the authors provided over the years. They provide, here are 3 example scenarios, inputs, outputs. The problems we find though, just in general, is that there's a lot of cases that aren't tested. And you'll get you'll get subtly wrong data. Slight changes in inputs can give large changes in outputs, and those kind of things that we don't like to have so much. And things that should be, I'm not talking about boundary conditions or singularities, things that should be valid conditions. Things that are not in any way straining the model will just give very unexpected bad data, and worse, like subtly bad data. That you don't know unless you're actually looking at it manually. That's what we would really like to try to avoid in our modern programs, and even in the long-running programs if we have the ability to add tests to them. So I think first maybe see what sort of validation tests or whole project tests there are. Maybe add a few more, and you might find things that are wrong, and then you can communicate that to the authors, or at least know that yourself, and you can kind of find a range. That's what I had to do for a project where I haven't had the ability to really interact with the authors, but at least I've been able to put on my website and communicate to people, hey, here are the range of inputs that we know are giving, subtly or significantly, but incorrect output. And at least we can know where the bad areas are, so to speak. And then if you are working with the internals of the program, so this might be something also too, if you have models or libraries that you use as a black box, where you don't, they're not, and maybe the model is not using an open source, or at least, they're not, they don't have, maybe the model is open source, but they don't have an ecosystem, like they just publish it, on a website, they distribute a zip file and an archive, but there's no pull requests, or, if you email the authors, they're very senior people and they're very busy, so, they may not be able to respond. So in a way, even though it might be open, the source is available, like you're not able to interact and fix it yourself. You just kind of treat it as sort of an open black box, one you can peek in, I guess a clear box, but one that you can't necessarily modify in an easy way unless you try to effectively you'd be forking the project, I guess, and to put it in modern terms. So you can do that for things that you have to make as black boxes or as an initial approach to a project. Then of course, I think the next step is once you do that, now you flip, what I do is I flip to the other extreme. I say, okay, here are some functions that are important to me, or functions that I think are buggy, or that might be troublesome, or that are just simple, like whether there's a lot of, whether they're troublesome, important, or it's just simple to implement. Like let's get our feet wet. And in this way also, when you're trying to get the project maintainers or the original authors on board, like sometimes they're like, I don't know, I don't really have the time for this. okay, but you can do this and I don't mind. You might start with something simple and say, hey, look, because you might find bugs, even though they're simple functions, and you might already start to find bugs. You say, hey, look, we need to make these fixes here. And that's been sometimes a way to get the original authors on board. And I've had cases where the original authors on a large project, like a 15-year-old project, were like, okay, I guess I don't mind. And then like in the course of a year, they went to like, oh my God, like now they're writing their own tests and like they've been, kind of converted them to the testing world. It's like, oh my gosh. And because it's actually saving them a lot of time too in the long run. And then so Python specific, I say, in my opinion, in a lot of big projects, including PyHC projects, are doing this, testing across Python versions and operating system versions. We do have some projects, including in our community, that, for example, might only work on Linux or Linux and Mac, and then they don't work on Windows very well at all or not at all. And in my opinion, that can be an issue because when we think about like undergrads and grad students, I don't know, this would be something good for a poll, I guess, in some way to poll the audience. How many people are running Windows? Like a lot of us that are more in the PyHC community, maybe a little bit more on the developer side, or at least, the modeler developer side, we might tend to run Macs and maybe Mac laptops or Linux and Linux HPC most likely. But your end users, or the new users, and at least a large subset of them are using Windows. So it can be a bummer when they're like, oh yeah, how do we, okay, first, step one, install Linux. And even though Windows has Windows since 2016, Microsoft Windows, they publish where you get from the Microsoft Store Windows subsystem for Linux. It's just an extra hurdle people have to do. And there are some projects, like I have grad students I work with, and I'm like, yeah, this project just doesn't. Even though it's a Python project, it does not work on Windows, and you just have to install Windows subsystem for Linux. But it's nice if we can avoid that. Yeah, I do. These are just things that aren't PyTest, but I use Flake 8, and of course, if you haven't used Flake 8, if you're like, oh, PEP 8 is too strict, you can pretty straightforward way configure Flake 8 to like be as lenient as you like. You can almost make it so all it checks for is syntax errors and things like that. But you can make it as almost as strict or as not strict as you like. And the same thing with MyPy. You can also make really make it like fanatically strict or a little bit looser. Just with a few parameters that are just really straightforward. And of course, I don't want to neglect, there's PyLint and there's many other checkers that I don't want to miss out on, but these are just the two that are fairly simple to use in my opinion.
Can I interrupt you with a question?
Please. Yes.
Yeah, Flake 8, you said you can customize it pretty endlessly, but out of the box, does it come just doing the PEP 8 checks?
Yeah, and it checks. I didn't think about the defaults. Let me just open up one that I use.
Yeah, I'm just thinking because
yeah.
I know part of our PyHC standards are that we want code to be following the PEP 8 standards. So
Right.
it would be helpful to give them a linter right off the bat that helps them with
Yeah,
that.
like here are Flake 8 settings, and I think I don't know if there's like a de facto standard in this. I think some like this, you can make it so that multiple programs use the same parameters, like to a limited sense, at least some of them. This is what I use. The same thing. It's very simple. This is just what directories to ignore. So just ignore this one. This is probably too long. Yeah. So you might say max line length. This is an older project, so I probably just haven't adjusted this. You can might make this 9. I think the black project uses 99. I think or 79
Okay.
or 99, but 89, whatever it is. Yeah. So you just decide what you want that line length, and then I say what I do is I make my init.py have these convenience imports. Like I break my Python projects or modules into like many files, and so instead of having to say import my module dot read, I have my init.py say from blah 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 import read, so that but what happens is then you get F401. It breaks PEP 8 F401, so I just say ignore that. But yeah, so we could anyway. I use this across almost all my projects. So as you see, I'm not really changing the defaults in any meaningful way. So yeah, I think just like projects will have like a Clang, C++ projects or C project will have a Clang format file,
Mm-hmm.
which those tend to be quite extensive. At least the ones I've seen. Flake 8 is usually we don't have to change. At least I haven't had to change the defaults very much. I am not a fanatical PEP 8 person at all. I don't. But I do try to make sure I'm using I'm not using 3 spaces instead of 4 or things like that. I don't want to mix styles.
Yeah.
So, and the same thing for MyPy. Like MyPy, I do adjust a few things. Most of these are just personal taste. Probably the most relevant one is this ignore missing imports. So, I mean NumPy, we're on NumPy 1.19 right now. NumPy 1.20, the next release coming, I don't know, in a few months
Mm-hmm.
or so, it will be MyPy enabled. So if you have, it used to be like the main thing is that most of my projects, is probably yours do too, use NumPy, and so it would just, if you run MyPy, it would be like, can't find, don't, module unknown or whatever. So I just carte blanche use this. Um, Although, yeah, I think Xarray, like Xarray has type hinting, PyTest has it, and NumPy will have it soon. So maybe in a couple of years this won't be as relevant. But right now I use import these things. These are just personal display options that aren't really that important. But
Yeah,
um,
great.
mhm,
Thank you for that.
yeah. So
I'm now over
go ahead.
here thinking out loud as to whether or not it'd be useful to just store in a repo somewhere some like config files for these linters that out of the box give you the PEP 8 kind of stuff. So people trying to submit code to our website, for example, we might say, hey, just use this config file and it'll just help you
Right.
make everything right. But
So depending, like, yeah, if you have like a self-hosted Git server, you can do things. I think what is it, post-commit hooks? You can say like, or actually, so people I know that are commercial, like that have their own enterprise Git systems, they will not. You cannot push the commit if the commit doesn't meet the project standards. It will bounce back. You actually cannot push that commit,
oh,
or merge that commit to master. So what I do, I'm just gear shifting since we're just talking about this. This is a little bit complicated. It's just a one-screen Python script. Every time I do git commit, this script runs, and you say, oh my god, I didn't actually prepare it for public consumption, but I'll just say briefly what it does. This is just check. So let's just start here. What it actually does, the first one does about four things. So every time I do git commit in any project, this is a global pre-commit script, and I have up above. I'll share this with the group. I'll share a link later to you can see the link, but I'll put it in the
yeah.
note. Every time I do git commit on any project, the first thing I do is I say, if it's a Python project, be sure I didn't leave breakpoints. I was doing that. So breakpoint is a Python 3.7 feature that it inserts a breakpoint. So I say, okay, don't, please don't push that to GitHub or whatever. So that's step one. Check for, debugging statements that will stop the code there. You can whatever, if in MATLAB this would be keyboard, if keyboard, that's the statement that stop, brings you into the debugger. The next step is I do PEP 8. So here it goes. It says if this is a Python project, run PEP 8. And if PEP 8 doesn't, if Flake 8, sorry, doesn't pass, then it will stop. It will prevent me from committing. The next step is probably obvious. I run MyPy. If MyPy doesn't pass, if there's any type annotation errors, do not allow to commit. Then I check YAML. So this is, again, each of these tests is independent, and that's why I could just note that they don't rely on each other. The next thing is I check my YAML. So as I'm going to discuss later, YAML is a frequently used to configure continuous integration systems. And YAML syntax is sometimes easy to make mistakes, or at least it is for me. So what I do is I do a sort of a trivial check just to be sure I don't have a very obvious syntax error. This doesn't actually like validate it. It just says, do you have a syntax error in the YAML or not? Then the final check is, so these were sort of Python specific checks. The last check is a generic check from Git, and what it says is there are no trailing white spaces and there are no excess blank lines at the end. Like sometimes you have you have 10 blank lines at the end of a
Nice.
file. This will say no, you can't. That's a personal standard, that I don't want trailing white spaces and I don't want blank lines. So this just makes sure. So you can adjust these. You could just this is just Python. Um, and people, what I found is that there were people out there that had done this in Bash, and I just said, well, why not? I'm doing it for Python. Why not just write it in Python? Because I wanted it to work on Windows was the main thing, right? Because I mostly use Windows. So yeah, this is pretty easy. It's like to start. I don't. This is just boilerplate stuff, and you can just kind of modify it. But that's so again, yeah. So if it was like if you had your own enterprise server, you can do this on the server side and say, But anyway, most of us aren't using that. We're using GitHub or GitLab, and so you can do it this way. Cool. That's
Yeah,
how
it's
I
pretty cool
apply.
to see.
And so here's the thing: you say, well, why? Well, you do that on the CI, right? So I do that on the CI, but the problem is, I do git push, and then I go have lunch, and it's like, oh, and I get all these CI because I didn't, it's like rather than have, and then then I'm making like oops commits or fix up commits. Like I try to keep my git history clean. I don't want to push when you have a syntax error. Then I feel like, oh, this is really silly. Like I have syntax error in my Python code, so I like to like catch it before I push it. I don't. You could run pytest. Now I'm not if you wanted to really get strict about it, you could actually say, add to that pre-commit, run pytest. Um, but for some of my projects, that takes like a couple minutes, so I don't want to have every git commit take a couple minutes. But you could, I think, actually, I don't want to misspeak. I would have to check. Could you make a project-specific pre-commit hook? That's an easy one to Google. I don't want to waste your time Googling it right now, but I could check. We could say, I think it has to be done on the user's computer. I don't. Anyway, let's think about that. If that becomes an issue, how we could. I know you can on the server side, straightforward, but anyway, think about that for the future. So Nick had jumped into this. I don't know if I want to repeat sort of what Nick said, but I just put a few bullet points, maybe that kind of that hit a couple highlights that Nick did. You know, that apply, as I said in the first slide, you know, applying these software best practices also benefits the testing and the testing, but it's like a happy feedback loop, a really good feedback loop where better testing makes better code and writing better code makes the testing go easier. Testable code generally tends to be maintainable code because if you've made it, if you've had, as Nick was saying, a separation of concerns, if you're avoiding side effects, you're avoiding state and functions except where you really want to, and avoiding global variables, you now have made code that's understandable, that's readable, so that you can have your grad student or your successor or colleagues, they can read it too. And if they question the behavior, they can look at the test. Like if you're completely unavailable, you retire, you move to some other field, they can, if nothing else, they can look at the document. Even if the document, sometimes the documentation is not, doesn't, the documentation often explains the interfaces, doesn't always really explain the internals, and so the tests can maybe help reveal some of that. Even though they're only testing from the outside, they can help reveal sort of what the expected ins and outs are. Functionize, packagize, methodize, whatever, just kind of using funny words there just to say just ways to make the code maintainable. Okay, so now let's get a little bit more specific. We're talking, continuing to dive more towards the practical. You know, many of you may know this stuff already, but for those that haven't, and certainly newer people to any language, this is true in any language. You know, you can find these trivial examples where 0.2 plus 0.1 is not equal to 0.3 in floating point. And certainly when you go to single precision, yeah, as I note here that, oops, I'm sorry, I should go back to presentation mode so I'm not wasting pixels. There we go. This will have a little bit better resolution for you guys. This is especially true once you get in. So what you may or may not realize is that in a lot of our scripting languages like Python, it defaults to double precision floating point, 64-bit floating point precision. So you can get away with a lot of things. Like there's, you know, you can think of these, you can find these little clever corner cases where you have 0.2 plus 0.1 is not equal to 0.3 exactly. This becomes much more of an issue when you go to single precision. And I don't know if in our field if we're using half precision too much yet, but there where there's really not very many decimal points of precision. And so you can run into difficulty because and this is maybe more of a compiled language thing, but it can happen actually in scripted languages. So I have had to do this even years ago in MATLAB. I was working with, you know, a very large, you know, I was doing a very large simulation working with large amounts of data. And what I would do is I would load the data from the file and immediately convert it to single precision and do single precision operations in MATLAB. And of course, you can do the same thing. And I've also worked with very large arrays in Python. And I actually intentionally, well, either intentionally or I store it for the same reason. I don't want to waste so much disk space. So even though that I use HDF5 files that are zip compressed, I also store it as 32-bit floating point to save space. And so in to save memory on the computer, I also in Python I try to keep on these programs working with large amounts of data. I try to keep the data 32-bit floating point, single precision floating point, which means again you have to be a little bit more careful with your quality checks and stuff. And that's not only that's you know in the you know not testing and in the code itself when you're trying to make it work, you be a bit more careful. And that's where you can trigger mistakes if you suddenly say, you know, oh yeah, this algorithm works fine, drop to 32-bit, and you know things don't converge and you're getting errors, and the program just stops working. So pytest assert handles this, helps handle this issue that it has built in. It has a finite tolerance. So let me just back onto this. Oops, back onto this here. Let's see if I can go to this link. I was just going to show the API. So what you have here is you have your expected, so you have two arguments, you know, as they show here. I'm sorry, one main argument. So they have the 0.1 plus, you see where I got the example around 0.1 plus 0.2. It is approximately equal to 3. So you require at least one parameter. You at least have to put in the expected value. And then you can input things like relative tolerance. You know, say I want this to be within 0.01. I want it to be within 1% of the expected value, or 5%, or maybe 0.001%. When you're working with functions, let's say you're working with trigonometric functions, transcendental functions, or just iterative models where the accumulated error is significant, yeah, you may want to. Sometimes I use a 10% error. I say if the result is within 10% of expected, because sometimes I work when you're working with different compilers and different operating systems and different libraries. Like there's many implementations of BLOS, for example, and some of them have different numerical methods that have different precisions. And when you do lots and lots and lots of operations, you could suddenly find out, oh, I need a 5% tolerance on this because across all these operating systems and library versions, and that can occur. Because you can compile NumPy yourself. So for example, if you're working in an HPC environment and you're really trying to get every little ounce out of NumPy, you may work with a custom compiled version of NumPy and you may have different tolerances because they're using, using Intel BLOS, for example, instead of netlib BLOS or whatever. There's like, I don't know, many popular BLOS implementations. They can relative absolute tolerance. You can say nons are okay, and so on. But let's hop back here. So I use pytest approx. I'm sorry. Whoa, that's a typo. pytest assert. Okay, I got to fix that. Sorry about that. This should say pytest. I even said that. I didn't even catch it when I said it. This should say pytest approx. Okay, I'll fix the PDF. This should be this is correct. This is not correct. pytest approx. That's the function we want to use. Okay, so now we're starting to dive into the Python functions themselves. How does pytest discover test? Like, so if I just, when I go to a project, I can literally just type pytest. Like if you go into many of the people that are using pytest or similar frameworks for PyHC, if they're using, for example, if they're using unit test, if you have a project that's using the Python standard library unit test, often you can just go into that directory and type pytest. You might get some errors because maybe they're doing something that's not pytest compatible, but generally it will at least mostly work. At least that's been my experience. So how does pytest or unit test or nose or these kind of things, how do they know? There's a de facto standard where pytest will first look for file names starting with test. There are some other, there are more rules in this. I'm just starting off with the most common ones. It will look through it will recursively look through the subdirectories in your project, find file names that start with test. Within those files, it will look for at least these three things: classes that start with test. It will look for functions starting with test. Oh, I'm sorry, these two things. It does not, yeah, you don't, I guess those two things are the main, these are the main three rules that it does. There are slightly, a little bit more it does, but these are the ones that I usually use. You don't have to use classes. You can just write, and I'll show some real life examples in a bit. You can just have strictly functions, or you can have test classes, or a mix. We use assert statements. So we say, as I did in this prior slide, with unit tests, you have to do things, like assert false, assert equal. With pytest, you don't have to use any of that. You can just assert. I write all kinds of tests, and most of my statements are like this. They're assert or variations of this. You don't have to have this assert false, assert this, assert that. You can just start with just a lot of assert statements. You can optionally pytest will, if you get an error, you can drop to debugger. Now that's probably not something you want to do on your CI, is let your CI hang, but you have that option. Like you can say, if not CI, you can drop to a debugger if that's what you want to do. There's hundreds of plugins. I mean, this is just one that I sometimes use, async.io. I don't know how many of you use async.io. It's concurrency in Python. But there's pytest timeout, pytest coverage, all kinds of them that we won't cover for time and scope reasons. All right, so now we've promised practicality. Here's a practical example. Let's start here on the left. This is the code on the right, obviously. So let's start with, how do we start from scratch? Okay, I want pytest. Okay, pip install python-m pip install pytest. You can use a pyproject.toml file. So just like we were showing with, we can use .flake8 and .mypy.ini files to configure default behavior. I like to use these up. So pytest by default will be very quiet. It will just show you a series of dots. It'll show, like each test it runs, it will show a little period, a little dot. I like to have it be a little bit more. Oh, actually, this. Oh, yeah. This is actually what this does. Actually, in my projects, I have it be. I have it be -RA-V, which is for the -V is verbose. I actually have it tell me. Instead of doing one dot per test, it does one line per test. I prefer that as a default. That's just me. But anyway, there's many options you can use, and so you can just, or you can also use pytest.ini. But and then so once you've installed and configured, if you need to, you just run pytest. Okay, so what would happen? How would we do this? So this is, imagine, normally this function, ×2, normally this would be part of your program. You would do like, import, my module dot ×2 or whatever. So you could put it in the same file just to make it simple. I made it in the same file. Okay, return 2 times the number. Okay, very exciting. So where it actually gets useful is, this is how you would test. So let's skip this parameterize right now. What I could do here is I could assert, let's pretend I'm going to ignore this right now. I could say assert ×2, 3 equals approximately 6. Okay, so that would be pretty much what you expect. Now, that gets pretty tiresome. Like, you pretty soon get tired of copy and pasting, assert, like 300 times typing assert. That gets a bit tiresome. So one of the key power features of pytest, or killer feature of pytest, is that you can parameterize. Now, this is pretty simple parameterization. What this is here, I won't dive into the syntax right now because we can click on that and look at that offline, is that it's just saying, test these. I have a tuple of lists. So this tuple says, for each set here, test them. So x is the input value. So assert that 2 times 5.5 is approximately 11. So 5.5 goes here because 5.5 corresponds to x, which goes here and goes here. 11 corresponds to y, which goes here and goes here. So 2 times 5.5, not exactly 11 in floating point, but it's pretty close. So we use approximate. If I did this, equals y, it would in general, it would throw an error. The assertion would not be true because of the floating point precision. So maybe so maybe, and obviously, like doing things much more complex than this, but that's the, this was the simplest example I can make that also showed the usefulness of using parameterization. Now, in reality, as I'll show in some real world examples, we do things like, test like different kinds of, maybe you test, text files and HDF5 files and this variable and that variable. We'll test all kinds of complicated things, but you have to start with something simple. And that's the link to pytest parameterize. So, which I used in the last simple example. So again, why do we parameterize? It deduplicates the test code, and it helps you make sure, because what's going to happen is you'll make mistakes in your test code. Because I've done this before I use pytest parameterize, I would be copying and pasting so much test code, and I would forget to include things that I always wanted to test this whole range of parameters, like good inputs, bad inputs, and I would forget to do that. So what I do, for example, I'll have functions that are test bad, and I'll have, here are all these parameterizations, each one of these should fail. Maybe, these parameters will give value errors, these parameters will give type errors, and you can do, I don't know if I show an example of pytest.raises. Basically, pytest will assert that a certain type of exception is raised. You can assert, oh yeah, if I put in a negative value, it gives me a value error, and that you assert that your function raises, or your class method raises that type of exception. You can also assert that it will raise a warning. I don't use that as often, but you can actually assert that your function gives a warning message if you input this value. And again, this obviously gives better test coverage. I don't know if we have time to jump into this, but you can look at that offline. That was this project that I'm showing here in this link used to use unit test, and I switched them over. Once they saw what pytest parameterizer they could do, they're like, oh my gosh, it was so much simpler to add lots and lots of tests. Okay, so here's another, now we're going to step it up just slightly in what I'm doing, still a pretty simple example. I wanted to show that, I think this is my only MATLAB example, an example from another language, but starting in about the year 2013, MATLAB added a much more powerful testing framework that's built in. But anyways, we're doing this, I tried to make it exactly the same, now I'm kind of testing my function that, I have this function called add. Again, normally this would be in another module. It would be not in the test program. It would be in your main program itself, or your main module. It just adds two numbers. Okay, so I'm going to test that it works with integers. Oh yes, in this case, yep, I add 1 and 1, and the result is 2, and it's an integer. I'm checking that that it is an integer, and here I say, oh, when I put in 2 floating point numbers, I get out a float. I could also test, integer plus float should give a float, and things like that. I didn't put the class examples here because in MATLAB, as you may know, if you use MATLAB, everything defaults to double. And you have to actually really try to keep things in integer. MATLAB keeps wanting to pop things back to doubles. That's a MATLAB quirk. So anyway, this is boilerplate. This is just what you have to do in MATLAB to make a function-based test. And then you can see here I do things like, oh yeah, I'm adding 2 numbers. I'm verifying they're equal. This is MATLAB's equivalent of a prox. MATLAB has this function called verify equal. And you can also, just like you can in pytest, you can specify tolerances. You can also specify tolerances in MATLAB with this built-in function-based testing. Okay. Import or skip, I'm just going over a few of the functions that are built into pytest. This is a bit overly complicated example, but I'm using a few things together, but I thought this is a real world example. I thought I'd just show it. So yeah, maybe you have oh my gosh, you have all this, these are just this is setting up the test, and then I'm parameterizing. I'm saying, for each, I'm going to find a whole bunch of data files. What this is, I have a project that has a bunch of test data files built in, and these files all have quirks or test different facets of the program. So first thing I do is I say, okay, take every data file and then parameterize based on that. So I say, find all the files in my test directory, shove them into a list, and then iterate over that list. So test I test I don't know, something like 100 files, I think. But the important thing is for this subset of tests, I know that I need netcdf4 library because these are netcdf files. So this will fail if netcdf is not installed and you already netcdf file, it's going to give an error. So what I do is I say, if the netcdf4 module is not installed, just skip. Don't fail, skip. And pytest will show at the end, when you run pytest, it'll say, this many tests passed, this many tests failed, this many tests skipped, this many warnings. And so this skips without giving a warning. Now there is something called xfail, for expected failure. That's kind of like skip and xfail. You can have xfail as things that are expected failures. again, this is a little bit of opinion, but so expected failures in my thinking, personal thinking, are for things that are kind of like on your to-do or fix me list. Like like let's say I have a project like I want it to handle netcdf files, but I'm not quite ready for it yet. So this is maybe not exactly right, but you say, okay, so if somebody puts a netcdf file in, it'll give you an expected failure. Now that's maybe not the best example. You might just want to skip, but anyway, you can think of things like where you want to put the test there to remind you, so you don't want it, like, so you could say, okay, this feature isn't ready yet, so I'm going to skip it, or you could say, like, another option is to say this is an expected failure because I haven't implemented this feature completely. Like I haven't, my program doesn't yet handle complex numbers. It handles real numbers, but it's not ready for complex numbers yet, so I'm going to make that an expected failure. And yeah, that's just another way to indicate what's going on. Because I think of skipping more like skipping is for the end user doesn't have this library installed, you say, well, why do you want that? Well, sometimes I have a big project, and you can, let's say I have a project that it can read text files, HDF5, NetCDF, MATLAB, IDL. Not every I don't want to make the users install SciPy and H5Py and NetCDF because all they want to do is read text files. So to reduce the number of my prerequisites for a Python package, I'll say NetCDF, H5Py, and SciPy are optional. And if you run the test suite, instead of giving you a whole bunch, if the user runs pytest, instead of giving a whole bunch of failures, it will just say skip, 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 because I don't have those libraries installed. So in my CI system, I also want to be sure in my CI that, because before I did this in my CI, what I would end up with is, because I always have H5Py installed for HDF5, I would have users saying, raising GitHub issues saying, hey, I don't want to install H5Py. I have like a Raspberry Pi or something. I don't want to deal with this installing H5Py. I just want to analyze text files. So this lets you conveniently have your CI be able to indicate, like, yes, you can run tests and be sure it works that it truly works without having all those prerequisites. Fixtures. This is a little bit more advanced than Nick was saying. Maybe this is a little bit, I agree with him. Maybe this is a little bit too much for this one, but I will just say that sometimes you want to generate test data. So sometimes the files you need are so complex you don't want to generate them on the fly, or they're just too hard. Because for example, I have a project that has like 200 tests and it's from GPS data. Like I don't want to try to simulate, right, like a GPS simulator to generate test data. I just want to save those Rhinex files. But in other cases, it is straightforward to generate test data on the fly. So you can do that with fixtures. I think there's more things you can do with fixtures, but I think the main thing, I'm going to think offhand, one of the main things I do with fixtures is generate test data that I don't want to have to save. Like maybe I want to generate like 200 different test cases, or maybe I want to generate random data. I want to assert that I can handle like all kinds of random values. I don't want to like save like 1,000 random data files. I just want to generate that on the fly. So you can do that with fixtures. So maybe I won't dive into the details just for time and to allow time for questions and not to bore people. This is maybe not something they use right now. I just will say that you can write fixtures in each test file, or if you make a conftest.py, that's a de facto standard. PyTest knows to look inside conftest.py for fixtures. Okay, let's give an example. Like talking about it isn't so illustrative, but let's do an example. So here I have a function that I'm assuming, yeah, here's my imaginary model, math fun. That's just a made up name, import fun. So I have a function that adds numbers. And so I'm testing that I can add integers and then I can add floats. So what I can do, in this case, I said, what's this here? I put in this, oops, sorry, I'm in the PDF, or I'm in presentation mode. What's this float gen? PyTest knows, this is a file is called testadding.py. PyTest knows, it doesn't see float gen in here. It doesn't see imported it. So it knows to go to conftest.py that's in the same directory. And it says, here we go. PyTest.fixtureGenerator, floatgen. Oh, okay, I will do this. I will emit 2 numbers. So here we go. I generate 2 random numbers, and it gives me 2 random numbers, and I can test that they add them. So I guess this would test, for example, that I can handle positive and negative numbers that are arbitrarily large or small. Because you could have, let's say, you could have a function that maybe, you may want to test it at known singularities, but maybe you want to do more than that. Maybe you want to just say, hey, I can test it with random values and be sure that the result is correct. This is a little bit of a trivial example. I think I show a more complicated, this is a more complex one. This is not something we would maybe use in our field, but I was doing this for a graduate course I was teaching. We were using FFmpeg, which is basically allows you to, among other things, convert media files. So this fixture was generating test videos. You could generate test videos with FFmpeg, and then the test part of the program, the students were required, they were compressing video, and then they would write tests like measuring like the SNR of the video, like saying, oh, their compression method wasn't too lossy, or wasn't generating files too big. So in this case, this is a way I can actually you can imagine, like, not, I mean, there's FFmpeg, maybe you have some binary, maybe you have some black box binary that will generate something for you. So you can use, sub process and run that executable with pytest fixtures to generate test data. Again, maybe a little bit more advanced for this discussion, but that's out there. Okay, so that was the end of my examples for pytest. I have a few slides on continuous integration, but I'd love to just take a pause since I've been talking a little over half an hour to see what thoughts people had or questions before I sort of wrap up with continuous integration. All right, sure. Well, see, I don't want to take too much dead air there. So, okay, so and I tried to make these so that people intentionally to make these so people could click on things. I tried to sprinkle links throughout so you could click on things and learn more about it. Just going to say, and I have some real life examples I'll finish up with at the very, very end. So just going to talk a little bit, sort of a brief survey of CI. Actually, this slide should be first. Sorry, I got these out of order. So continuous integration, there's a lot of paid services and there's a lot of free services. I'm going to discuss the services that at least have a free option. Historically, one of the favorite options, going back even several years, was Travis CI. They had a good integration with GitHub. They will now work. I think they also work with Bitbucket. They integrate with more than just GitHub now. Historically, they were just GitHub. So Travis CI was kind of one of the one of the early and great free CIs. There were others, but they were one of the great ones. Very in the sense of being very popular. But originally they were Linux only. AppVeyor came out and they were Windows only, but they had, so when you wanted to test, I had a lot of my projects, if you go back in my Git history, like 3 years, I will have a lot of my projects back then had Travis CI for Linux and Mac, and they also Travis CI then, and after a while added Mac. And then we had AppVeyor for Windows. Now after a while, AppVeyor added Linux and Mac, and then Travis CI added Windows. So now they both have Linux, Mac, and Windows. AppVeyor still has maybe more features on the Windows side. They have lots more variations of Windows you can work with. That maybe is a little bit less relevant for our field, like we're not, making video games or things we need to worry about, exactly which version of Visual Studio and stuff you have. But if you do have a Windows-centric program, that would be for you, perhaps. And then Microsoft brought out Azure Pipelines, which is very powerful. It's more complicated to use than Travis CI or AppVeyor, but I would just say it's very powerful, very, very configurable. So once I outgrew, the problem with Travis is, this is a personal opinion again, I think they're a great service. Once you try to go beyond a certain amount of complexity, you hit a brick wall. So, a simple YAML syntax starts to become constricting. This is not a harsh criticism. It's just that what I observe is that it starts to get difficult to do things in Travis. And what I found is that even though Azure is more complicated to use for simple projects, it actually becomes simpler to use for complicated projects. So at a certain point, this Travis became too hard for me. And I was running into bugs in Travis, unfortunately, so I had to switch to Azure. So I switched to Azure for a while, and then I think it was last August, GitHub Actions came out. And for me, this was like Nirvana, Shangri-La, whatever your favorite euphemism is. And what happened is I went from all my projects, you will see in my Git history in the past year or so, have gone from Travis CI to Actions, AppVeyor to Actions, Azure to Actions. Because this, for many applications, it's powerful and relatively easy. Not as easy as Travis, but in my opinion, easier than AppVeyor or Azure. Circle CI I haven't really used as much, but they are something that's also used in our community, and they're very powerful as well. I just don't have the experience with them. So I put GitHub Actions. This is just personally not because they're the greatest of anything, but because I happen to use them the most of all. So just to hop, now I'm going to hop back to this slide. So they typically, how do you configure them? Usually you use something called a YAML file, which I'll show an example of in a couple slides. And these are just the names like Travis, AppVeyor. If you wonder what this is in a project, I put these here. If you see them in a project, what's this? This is what they are. And so again, they let you iterate over Linux, Mac, and Windows. Travis CI also lets you iterate over CPU types. You can do IBM Power processors. I don't know if that's necessarily relevant to what we're doing in Python, although I guess there is, coming up at our hackathon, there is a project that wants to use ARM. So you can do ARM, you can do x86. I think they have ARM and IBM Power. So we have different Python versions, of course, and different compiler versions. And sorry, I put the processors down here. And these are some of the most popular, probably the 4 most popular open. They're not open. These 2 are open source. These 2 are not open source, but they are free to use. Free, but free, small f free, no charge free. And Intel, so if you may say, wait a minute, Intel's not free. Yes, so Intel One API came out this year. Historically, for many, many years, going back and then going back decades when they were DEC, I think the DEC compiler kind of morphed into the Intel compiler, or at least there was some shared heritage there back from the 80s. But for many years, Intel has been a paid compiler. Intel One API is actually free to use for anyone, and that's just coming out that just came out this year. It has the same methods of invoking the same options. It's just free of charge. Maybe just to save a bit of time, I think this is something we don't have to talk about here because many of us are just using Travis or GitHub Actions, so I'll just leave you that's just for offline purposes. Oh, one thing I do want to note about is that if you are a MATLAB user and you want to do CI in MATLAB, starting at the end of summer, actually early this fall, there wasn't a big announcement about this, but I did run into it, that starting in September or so, the past couple months, you can use MATLAB on Travis, Circle CI, or Azure. MATLAB is much easier to use on Travis CI than these other two. That's, again, just a personal opinion. So, okay, let's just do a basic example here. Now, do I have a Travis example? Let me start with a Travis. Right? Travis is simpler. So you see how simple Travis can be, and this is why it's been so popular. Many of our PyHC projects use Travis. You just say, okay, step one, this is your .travis.yaml file. Language Python, what Python versions, install the program in the prereqs and run the script. Kind of hard, I don't know how much, I mean, that's even simpler maybe than talks.ini. And some people also, instead of iterating over it in Python, people that use talks will iterate over it using talks.ini. That's another way to do it. Some of our PyHC projects do that. And you say, okay, why do this instead of this? Why do I want to use GitHub Actions instead of this? It's because, I guess, in general, when I want to do things, now this project, yeah, this project is just quite simply easier to do in GitHub Actions. Well, I guess, okay, here I am iterating over Ubuntu, Mac, and Windows. So yes, it's not quite fair. I would have to add several more lines if I was doing Mac OS and Windows. Travis CI, like many CIs, defaults to Linux if you don't specify it. So if I wanted to iterate, I'd have to add more lines here to do Mac and Windows. So, all right, maybe it's a toss-up. GitHub Actions here, this is actually a very simple project to test. GitHub Actions is probably going to be a little bit more complex no matter what. It's when you start to do, which I don't have time for today, when you start to do compiled libraries like you have C or Fortran code you want to include, that's where GitHub Actions starts to become much more friendly to use. But you can just see here basically iterating over, I'm using Ubuntu, Mac, and Windows, and I'm using different Python versions. And finally, we just have, this is the last couple slides. If you're really advanced, you might end up using Docker. I don't know if anyone in our community is doing, maybe the Resin project, I guess obviously they're using Docker. So maybe we have a couple projects that are getting this complex where they need to use Docker, like where you would basically do this if you had such a complicated setup, like if it takes your CI image like a few minutes to set up. It is typical to take the CI image maybe one to 2 minutes to set up, like you need to install a Fortran compiler or whatever. But if it's starting to take you like 10 or 15 minutes just to set up your CI, like that starts to get impractical. That's where you might use a Docker image, where advanced CI users will set up a Docker or a Singularity image or a Resin image or whatever this will basically install much faster, or can for big things. Finally, we have just touching on continuous delivery. This is where you can actually, for best practices, if your project is big enough that you're distributing binaries, you're distributing wheels or things, you want to do that really in a CI system. You don't want to do that on your laptop. First of all, is for security. If your laptop gets hacked, maybe you're distributing viruses to thousands of users and you're infecting, agencies and all kinds of stuff, and you would probably feel pretty bad about that. So in this case, you're shifting the responsibility to the CI provider, that their CI images are, they have staff. Hopefully their CI images are virus-free and things like that, malware-free. And this way, we're not counting on, what if you drop your laptop or if somebody leaves and now, oops, we can't build our program anymore because, so-and-so left and they're not here today. All right, so I'm just going to show, just a few more minutes here. I was just going to show some examples. Oh, I just was going to give some news. Now let's kind of flush our brains a little bit. We had a lot of technical content. Just for a little bit of tech news, things that came today, October 29th. Just says Ubuntu 20.04 has been available in GitHub Actions for a few months. This notice that came out today says that as of November 30th, GitHub Actions is going to default to Ubuntu 20.04. You say, well, okay, why isn't that obvious? We should use a recent version. No, back when I was using Travis CI for a very long time, the newest thing you get on Travis CI was Ubuntu 14.04. That was one of the things that drove me away from Travis. Like now they're up to date now. Now you can get a current version of Ubuntu, like I think at least you can get Ubuntu 18.04 on Travis. When you're doing compiled stuff, when you're trying to use Fortran code and C code, and you have to use really old versions of GCC, it gets really painful to do that on Ubuntu 14.04. So that's why this is relevant. If you're doing something with, if your library involves compiled code, this is stuff that helps you to use a more recent version of Ubuntu. The other thing is that if you're doing stuff on Mac, compiled stuff on Mac, I'm excited about this because I've been looking at getting a new Mac just for the purposes of testing on Mac with Big Sur. So here we are now. Okay, now I don't have to, I can maybe save $1,000 and do that testing on a GitHub Action. So it's now available in preview. If you're those of you doing compiled libraries might appreciate that. I'm just going to close these windows to reduce the clutter here. I'm just going to say I mentioned that I'm just going to touch on a few scattered topics here before we hand it off to the next speaker. I did mention that Travis CI uses MATLAB. So for those of you using MATLAB, this is a more advanced setup, not advanced, like an intermediate setup. So we say, okay, dist bionic. I had to do that because the MATLAB on Travis CI is R2020A, and that there's lib standard C++ needs Ubuntu 18.04. So if you're doing the default, if you're not mixing compiled code, maybe I'm kind of the oddball here that mixing compiled code with MATLAB programs. That's what I do. So I had to make it compatible, I had to go to Ubuntu 18.04, language MATLAB, latest version of MATLAB, which for them is right now R2020A, Linux, of course, and this is just default Git parameters. And then here's the things I'm using. My program uses Fortran, HDF5, LPAC, and BLAS, and OpenMPI and mouse. So this is what I had. So then the problem is, like, these are some of the tricks you have to play. I show this not for just idle time, but one of the issues is that a frustrating thing. One of the things that frustrates me about Travis is they have a really old version of CMake. Even though it's Ubuntu 20.04, they put an old version of CMake on it. I don't know why. So Craig Scott, one of my CMake colleagues, has made this snap available. So this is, if you need to get some library that's more recent, you can use snaps on Travis. Snap is like a method of installing an isolated package on Linux. You can do that. And then I just have to put, here I'm doing is like I'm putting snap on my path, my system path, and then I have a script called testall. I have testall.m that invokes a whole bunch of tests. So I don't know, again, I don't know how many here are MATLAB users, but I know it's used in general, sort of in engineering, and I won't go into the syntax. This is how you set up a basic sort of CI-friendly test on MATLAB. All right, so just to show more, I'm going to close some of the tabs here we don't need. I'm just going to show, here are some more import or skip examples. So I have a program called PyMap that has, I don't know, a few 100,000 downloads, I think. Let's check. Okay, over 400,000 downloads so far. So I have all these tests. These are all my test files, and each one of these test files, this is a practical real-world example that hundreds of thousands of people have downloaded. So each one of these files tests a different aspect. Okay, so this is a pretty small file. I test this Vincenti function, and I didn't I guess I was kind of lazy this day. I didn't parameterize it. Let's go to one of the better ones or actually do some more that's not a very good test example. I should be testing more than one data point. Okay, so here I tested 2 data points, actually the same data point. This is an example. So I want to test that these functions, this is a geodetic ECEF. Geodetic is like latitude, longitude, altitude. ECEF is the XYZ reference to the center of the Earth. So I said, okay, I want to test that it works with scalars, and I want to test that it works with lists. Well, I guess, yeah, here's the IDs. Some of these, okay, so here I didn't prepare this well enough. There's somewhere I have more oh, here we go. Here's one where I'm testing singularities. I want to test like that this works at 0, 0, 0, 9, like at the poles and different places on the equator. I want to be sure that it's just stable. So here's an example of using a test to test. Now I didn't do the thing. What I was saying with Nick is that I didn't yet implement where you do this, 0, 0.0, 0, 1 times 10 to the negative 16, 10 to the negative 15, so on, like 0.11. I didn't implement that here. I implemented that on one of these functions, but I don't remember which one it is offhand. But that's, yeah, so each one of these functions has lots of tests. Yeah, this is the example of that pre-commit script. I showed that already. We'll close that. This is another example of using parameterizations. Anyway, that's just another example of testing a whole bunch of parameters using different types, testing parameters. I'll link these in the presentation. I think that's actually the end of the examples and stuff. Just wanted to throw a potpourri of those out there. I'll put the links in and I'll read it. I know I had a mistake in there I found earlier. I'll add those potpourri, those zoology of examples, and we'll be good. So I'm trying to think of any final comments. Yeah, so I just think, this can be very overwhelming at first, but I just say start small, start testing a little bit, test a few things, test the whole program, test a few known inputs versus known expected outputs, and if it's not your thing, you say, oh, this is too boring. Maybe you'll find someone else that likes to do a pull request or something, or at least it'll help you address bug issues, as Nick was saying. Thank you very much.
Well, if we don't have any more questions for Michael, we could just slide into Eric's tutorial or take a minute or two break and let people get up and walk around.
I have a question for Michael.
Yeah, go ahead.
It's about pytest. So is there a way to get pytest to ignore, say, like a SymPy version error and just make it keep going anyway?
Yeah, I guess I'd have to know a little bit more. Like, does it raise an exception like value, like it raises value error, or?
I have to run it again.
Yeah, it's okay. It's okay. Yeah. Feel free to reach out either via I don't know if you're on the Element channel, the Element/Matrix, or via email. I'll post my email in the chat. I didn't put it on the presentation slides for shame. I'll have to add that too. But please feel free to reach out via email, which I put in the chat, or via the Element, or however you like. I'll be happy to take a peek. What's going on?
One other question. So you mentioned PyMap does a lot of coordinate conversions. How would that compare to other software that's out, like Geo?
Yeah, that's a great question. So I actually addressed that. This was published in the journal JOS, or Journal of Open Source Software. Actually, I put a statement about that here. Let me see if I remember what it was. So the advantage, oops, looks like I put that somewhere else. Anyway, so the main thing is that it does, so PyProj projection is very popular, but it requires you to have, I think, GDAL and some other compiled libraries installed. This is just pure Python. It doesn't even require NumPy. So I wrote it that it doesn't use just Python standard library. It will convert. Now, normally people will use NumPy with it because they want to use lots of, they have like arrays of values. And so this works with n-dimensional NumPy arrays as well as Python lists and Python scalars. It has, yes, I'd be happy to hear maybe there's something better out there. There probably is. I think this is a little, oops, I'm not sharing my screen, sorry. I'm just going to show some of the functions it has. See if I've got the right, yeah, there we go. I made it have a very similar nomenclature, I guess, API nomenclature to MATLAB, so that because people that have used MATLAB will tend to search for these functions. So I didn't, people that haven't used MATLAB are like, why did you pick these weird names? I didn't pick them. It's ones that MATLAB uses, and I tried to make their interface similar. Because at the time, I wrote this years ago, like back in 2014 or something. I was a heavy MATLAB user, and I was switching to Python, so that's what it was. Like, I used these functions for years and years and years in MATLAB. I said, oh, I want them in Python now, so that's what I did. I made them. Because people have said, like, why don't you make this object-oriented? There would be various efficiency gains from some of the, because it's purely purely functional, but it's I don't want to say it's purely functional, but it's all functions. There's almost no objects in there. It does some computations repetitively that it wouldn't have to do if I was using objects. So. But that's it. That's it. It's basically that you don't need anything but the standard library, and it can use NumPy or Xarray or SciPy. Kind of, yeah.
Okay,
Classic.
thank you.
Yep.
Any other questions for Michael? If not, go ahead to Eric. Thanks, Michael, and also Nick, although he's not here, for your great tutorial.